let's just get one thing straight right from the start. 100% uptime, it's a myth. It just doesn't exist. So the real goal for any cloud architect isn't to prevent failure. No, it's to build systems that expect failure, that can embrace it, and most importantly, survive it gracefully. Today, we're going to dive into exactly how you can do that on AWS. Okay, so let's get into it. Meet the main character of our story today. A pretty standard, everyday microservice application running on AWS. Looks familiar, right? You've got a load balancer out front, some API services doing their thing, back-end logic, and of course, a database. It looks clean, it looks stable, but it's hiding some pretty dangerous secrets. And that really is the million-dollar question, isn't it? What happens when the inevitable finally occurs? You know, when a server just gives up, a network connection gets spotty, or an entire data center just has a really, really bad day. This is where things get interesting. Let's start with our first disaster movie scenario, the big one. An entire AWS availability zone, or AZ, suddenly just goes completely offline. Now, remember, you can think of an AZ as a whole separate, isolated data center. So we're not just talking about one server failing here. We are talking about a massive, widespread outage. So what happens if our entire application, every single server, every database instance, the whole shebang was running inside that one AZ? Well, it's pretty simple. We're completely down. Game over. Our users are just seeing error pages. The business grinds to a halt. It is, without a doubt, the architect's worst nightmare. So how do we fight back? Well, our first line of defense is a multi-AZ deployment. The idea is simple but so powerful. Think of each availability zone as its own little island, a physically separate and isolated data center. So by spreading our application across multiple AZs, we're creating these isolated failure domains. And that means a fire, a flood, or a power outage in one AZ, it's not going to touch the others. We've just contained the blast radius. And here's where the magic really happens. Our Elastic Load Balancer is constantly, and I mean constantly, running health checks. It's always pinging our servers to make sure they're alive and kicking. The very moment it sees that all the servers in, say, AZA are unhealthy, it automatically and instantly stops sending any traffic there. All of your users get redirected to the healthy servers in the other zones. And the best part, your users never even knew there was a problem. Okay, so surviving a big outage is one thing. But sometimes the more dangerous problems are the smaller, more subtle ones. So let's look at our second scenario, the domino effect, where one tiny failure in a single microservice kicks off a massive chain reaction. This right here is the core principle of building resilient microservices. I mean, imagine a recommendation service fails. Now, if every other service that calls it just sits there waiting and waiting for a response that's never going to come, they tie up all the resources. Pretty soon, they start to fail too, and that failure just cascades across the entire system. And just like that, one little hiccup has caused a total application meltdown. So how do we stop that domino effect? Well, we use a really cool pattern called a circuit breaker. And honestly, it works exactly like the circuit breaker you have in your house. When it detects way too many faults or, too much current, it trips and it cuts off the connection to protect the rest of the system from damage. Now, this circuit breaker has three main states. Normally, it's closed and all the traffic is flowing just fine. But if the error rates get too high and pass a certain threshold, it trips to open. Now, all calls to that failing service fail immediately. They don't even try, they don't wait. This is so crucial because it protects the service that's making the call. Then, after a little timeout, it moves to half open, where it lets just one single test call through. If that call succeeds, great, the breaker closes and things go back to normal. If it fails, the breaker stays open. It's a super smart, self-healing mechanism. All right, another really powerful pattern for isolating these kinds of failures is called the bulkhead. And the metaphor here is just perfect. Think about a big ship. The hull is divided into these watertight compartments. So if one compartment gets breached and starts to flood, the bulkheads contain that damage, and the ship stays afloat. We can do the exact same thing with our software by creating separate resource pools for different services. And what's really cool is how you can apply this exact pattern across all sorts of different AWS services. If you're using EC2, for instance, you can use separate auto-scaling groups for your services. For containers on ECS or EKS, you can set really strict CPU and memory limits. And for Lambda, you can use something called reserved concurrency to put a cap on how many executions a specific function can consume at one time, which prevents a runaway function from hogging all the resources and taking everything else down with it. Our final villain is maybe the most insidious of them all. It's not a service that fails hard and fast. No, it's a service that just gets slow. It's still up, it's still responding, but it's just dragging down the entire user experience with every single call. See, an outright failure is actually pretty easy to detect. A circuit breaker will trip, health checks will fail, alarms will go off. But a slow service, that's a silent killer. It just hangs onto connections, it consumes threads, and it causes timeouts and all the services that are trying to call it. It leads to this frustratingly slow, awful experience for the user. And in many ways, slow is so much worse than down. So the answer here is to design for what we call graceful degradation. All that really means is your application can fail smart. For example, if that recommendation service we talked about is being super slow, don't make the user wait forever. Just set an aggressive timeout. If you don't hear back in, say, 200 milliseconds, just give up. Render the rest of the product page without the recommendations. The core function is still there, and the user's experience is saved. So as we've walked through all these scenarios, you can probably see that resilience isn't some single feature you can just turn on. It's a mindset. It's a whole collection of patterns that you apply throughout your architecture. So let's pull all of these big ideas together into one simple, actionable checklist for the modern architect. Here it is. This is your playbook. This is your starting point for building truly fault-tolerant systems. Always deploy across multiple AZs. Make sure you're using health checks to automatically route around failure. Be aggressive with your timeouts on all network calls. Wrap your critical dependencies with circuit breakers, isolate them with bulkheads, and always have a plan for graceful degradation. This isn't just a list, it's a whole new way of thinking about how you build software. And that really brings us to the final thought. After you've architected your system to survive all of these common failures, the work is not done, not even close. The real question you should always be asking yourself is this: what's the next thing that could break? A truly resilient system is never finished. It's always evolving.